Hi, everyone. I'm Aparna, and today I'll be talking about my work on classical obfuscation of quantum circuits via publicly verifiable QFHE. And this is joint work with James Bartusek, Sachi Matreja, and Omrish Muali. So thank you for having me. Okay, so the protagonist for this talk is going to be something called program obfuscation, which is this tool in cryptography whose goal is to make programs unintelligible while preserving input-output behavior. So, on the left-hand side, there's this simple program that just prints the string "Hello World." But on the right-hand side is an equivalent program. It does the same thing, but if you're like me, you would have no idea that that's what it does. It doesn't even have the words "Hello World" written in it. So this is an interesting curiosity. Why do we care? Well, things start become more interesting if you have more interesting programs on the left. For example, this program that checks, whether you inputted the correct password. This has some secret information. So it would be really nice if you could obfuscate it in a way that hides what the password is. And this is why it's such an important tool in cryptography. It's so powerful that it's, considered to be crypto complete. Obfuscation of programs with just very minimal other assumptions basically give you everything that a cryptographer could dream of. So it gives you, public key encryption, the bread and butter, but also more exotic types of encryption like fully homomorphic encryption, witness encryption, fancy proof systems like SNARKs, and even things like software watermarking. So this is a really important tool in cryptography, but does it exist? Well, a few years ago, this breakthrough work by JLS constructed obfuscation for classical circuits under standard assumptions. Never mind that they're quantum broken, but this was a huge breakthrough. And so now we have obfuscation for classical circuits. Okay. So, now can we...
So what is the state now? Do we know how to do obfuscation of classical circuits from quantum safe assumptions as well? What is the state of the art now? Do you know?
Yeah, there are more candidate constructions, but they're all they all introduce new assumptions that perhaps weren't studied as well before.
I see. Yes. Okay, thanks.
Yeah. Okay, so we have obfuscation for classical circuits. Can we now obfuscate quantum circuits, right? So the goal here is you're given an input quantum circuit, its description, its gates and wires, and then now the goal is to convert it into an equivalent circuit, scramble it so that you hide implementation details. And hopefully you end up hiding any sensitive information. So, you might be wondering, this seems like a premature question to ask. We don't even have a great handle on post-quantum obfuscation of classical circuits. But here's a question we can ask. Assuming we did have post-quantum obfuscation of classical circuits, can we now build obfuscation for quantum circuits? Right? So really trying to understand the gap between what you need for obfuscating classical circuits versus quantum circuits. Okay, so this title had two terms, obfuscation and quantum circuits. So let me be a little more concrete about both of them. So it took some time for cryptographers to come up with, what exactly is the right notion of obfuscation. How do you know, what counts as a secure obfuscation? How do you know that a program isn't scrambled enough? And eventually they converged on a definition called indistinguishability obfuscation. And this is the right definition to look at. But for this talk, we'll consider a simpler idealized notion of obfuscation, ideal obfuscation. So what is this definition? This says that an obfuscation of a circuit is as good as an oracle for that circuit. Right? So anything you can learn from the obfuscation, you could have just learned with oracle access to C. Another way of saying this is the only thing you can do with the obfuscation is evaluate it. There's no other secret information that leaks, right? So in cryptography, we think of everyone as an adversary. So in this picture, the adversary is given an obfuscation of the circuit, and on the left-hand side, and on the right-hand side is given access to the oracle for C. And it should everything it can do, everything it can output on the left-hand side can also be outputted on the right-hand side, basically.
So I have a small question. So we are talking about obfuscation of circuits. Why don't we start with the states itself? Because this seems, I mean, this will include states in it, probably more like relevant computation as well. But why don't we start from states only? That we want to hide the state in some sense.
Like a quantum state, or?
Yes.
I see. So you're interpreting the quantum state as like some auxiliary input you feed to a circuit, and is that the idea?
Yeah, and the circuit I want to take trivial, because the quantum information you can store in state itself. So I want to hide that information or obfuscate that information. But here it seems that you care about the circuit as well. I mean, they are equivalent in some sense. So I'm just trying to ask that if I don't perform any useful computation, and still talk about the obfuscation of some particular kind of state, for example.
How is that different from encryption?
Yeah. To make sure I understand, like, are you looking for just something that hides what a quantum state is?
Yes. So
yeah, that you can do with just like scheme. You don't need to go all the way to obfuscation. Like if you apply a random Pauli to the state, then that actually creates the maximally mixed state. So that's an encryption scheme where the keys are like which Pauli you applied.
Okay.
Yeah, obfuscation allows you to do something stronger. Like, sure, you can encrypt a state, but there's not like you can't do anything further with that. Obfuscation like allows you to treat the thing you're encrypting as a circuit and actually evaluate it and get outputs in the clear.
Right. Thank you.
Right. So, and we're looking at a very idealized notion of obfuscation, where you're thinking of the obfuscation as being as good as just an oracle. And okay, so it might not come as a surprise, but this is an extremely strong notion of obfuscation, and it's impossible in general. But for us, it will be a useful simplification to understand obfuscation of quantum circuits. Again, like we're really looking at the gap between obfuscating classical circuits and quantum circuits. So we're trying to isolate that question and keep everything else simple. Okay, so, now the goal is, concretely, assuming you had ideal obfuscation for classical circuits, can you get ideal obfuscation for quantum circuits? And what that effectively means for us is that, if we have ideal obfuscation for classical circuits, that effectively means that we have classical oracles for free, that you can use these classical oracles to compute, to like give black box access to any efficient classical function.
Can I ask? Sorry. Go ahead. Whoever was that.
Can I ask why is it impossible? I mean, you said in the previous slide. You said that ideal obfuscation is impossible. Why is it?
Yeah. Okay. So one thing that I guess one way to look at it is that the obfuscation is something you generally write down as like as text or something, but an oracle, it's like a type mismatch. Like on the left hand side, for example, the adversary could just like output the program description, like output the obfuscation, and then I would have a description of the program. But on the right hand side, just given this oracle, it has to somehow extract a like source code of the program, which is impossible in general.
Oh, okay. Yeah, thanks.
Yeah, no worries. Atul, do you have a question?
So I was just trying to understand what is the right way to think about building something from something that's impossible.
Yeah. So I guess one way to look at it would be like a more plausible notion of obfuscation, like indistinguishability obfuscation, is like a heuristic instantiation of ideal obfuscation, right? So if you had this translation between ideal obfuscation of classical circuits to ideal obfuscation of quantum circuits, you could hope to replace that ideal obfuscation with something concrete, like an indistinguishability obfuscation scheme. And then you could hope that, okay, this might translate to indistinguishability obfuscation for quantum circuits. We don't have that kind of result yet, but you could hope that
it's just like formal evidence in that direction that somehow it should still be secure and we have like some kind of a proof. Is that the way to think about it?
Yeah. Yeah. Like another way to think about it is, okay, you have some obfuscation scheme for quantum circuits, except there are these classical oracles thrown in the mix. Now you can get like a heuristic obfuscation scheme for quantum circuits by replacing the oracle with whatever actual obfuscation you have.
It's kind of like the random oracle heuristic.
Yeah. Yeah. Okay, so yeah, so we get classical oracles for free when we're trying to build this obfuscation. And let me be slightly more precise about what I mean by a quantum circuit. This came up a bit earlier. So when I think of a quantum circuit, I usually think of, wires and gates that describe what the circuit is doing. But another type of quantum circuit is something that comes with an auxiliary quantum state, right? For this talk, we'll be focusing on the first kind of circuits. Okay, so what is known about this question? Over the years, there have been more and more works that, build obfuscation of quantum circuits with increasing like complexity. So we started out with BK21, unitaries with only log many T gates. And then there was this work on pseudo-deterministic circuits. And then finally, just last year and this year, there was very nice work on obfuscation of unitaries and even more general quantum circuits. So for us, an important class of circuits is going to be this pseudo-deterministic circuit class. And what that means is that it's a quantum circuit that computes a classical function f with negligible error. So this is an extremely expressive class. It, for example, it contains all of NP that has an efficient quantum algorithm. And in particular, it contains Shor's algorithm. Okay, so an interesting property of all the known obfuscation schemes, previously known obfuscation schemes, except with the exception of like BM22. But all the others have the property that even if the input quantum state has a completely classical description, when you obfuscate it, the circuit turns out to be, it turns out to need a quantum auxiliary state to be able to evaluate. Right, so this obfuscated circuit no longer has a classical description. In particular, the obfuscating algorithm itself has to be quantum. So this was true for like all the previous work except for Bartusek and Malavolta 22, who constructed obfuscation for null circuits. But for all other circuit classes that are like more expressive, like null circuits just always output 0 on all inputs. But for more expressive classes, this was always the state of affairs. Okay, so this is not ideal because now you need quantum communication channels to send an obfuscated circuit to someone. But more fundamentally, it raises the question.
This is about the previous slide before we move on. I was trying to understand what it means to obfuscate a null circuit. So is the requirement that it's indistinguishable from any circuit, or we know that it's within that class? Like, for example, if in any of these, like if, for instance, if you give me a pseudo-deterministic circuit and you give me the obfuscation, is it the case, is the guarantee that I don't know among pseudo-deterministic circuits which pseudo-deterministic circuit is sitting inside, or I cannot distinguish it from any quantum circuit?
Okay, so yeah, you won't be able to get a guarantee that says you're not able to distinguish it from any pseudo-deterministic quantum circuit. I guess it depends on the notion of obfuscation that you're going for.
Shoot, yeah, maybe I'll think of something wrong. Yeah, okay.
For example, yeah, if you were looking for indistinguishability obfuscation, which is implied by ideal obfuscation, I think what you're saying is that for every two circuits that have the exact same functionality, the output.
You can't distinguish them.
Yeah. So it's immediately not clear that it's a useful notion, but yeah,
I see.
Yeah, but it turns out to be very useful in a lot of settings. Okay, so previously the state of affairs was that the obfuscated circuit always came with this auxiliary state that you needed to evaluate it.
Oh, I'm sorry. Can I ask a follow-up? I promise I'll let you move on after this. Okay. So what I'm getting a little bit confused with is that normally when we think of regular encryption, right, the message space always has to be non-trivial, right? Like if there's only one message that I'm sending, then obviously I cannot encrypt it. So I'm getting a little bit confused about how to think about null circuits. Because a null circuit is just like, it looks like it's a singular circuit. So what is, how can one possibly hide that, right? It's not very clear to me. Unless you're hiding it among, from any other potential, like, I don't know.
But I think if you're thinking in terms of like virtual black box, you're thinking like some stronger functionality than what IO actually gives you.
So sorry, I didn't catch that. Can you say it again, please?
So I think you're still thinking in terms of like that much stronger virtual black box obfuscation functionality rather than IO.
Okay.
So you're not trying to just hide all the details of that computation among the entire class.
Got it. Okay. Sorry.
Different slightly.
So among all implementations of that specific null circuit, I won't be able to tell which implementation is being used. That's the idea. Yeah. Okay.
If you are given to circuits that compute this null computation, then you cannot know which one it is. So
got it. Yeah. Sorry for being dense about this. Okay, thanks.
No, all good. Okay, so this raises the question that does obfuscation of quantum circuits fundamentally need the obfuscator to be quantum? Especially if you're like trying to look at circuits that are more expressive than null circuits. So in our work, we show that no, at least for the class of pseudo-deterministic circuits, there is a classical obfuscator. Okay, so in more detail, we show that assuming the quantum hardness of learning with errors, and in the classical oracle model, there is a classical obfuscator for pseudo-deterministic circuits. And the main workhorse we use to get this result is something called publicly verifiable quantum fully homomorphic encryption for the same class of circuits. I'll define what that is later. And then as additional contributions that might be of independent interest to quantum cryptographers, we get post-quantum succinct ideal obfuscation for classical Turing machines using techniques from CMS and Chandri. And finally, this gives us the first succinct randomized encodings for this class of circuits, pseudo-deterministic quantum circuits. I won't talk too much about the second two results. I'll mostly focus on the first two.
So, sorry, go ahead.
I was just going to ask, just to verify that classically, when you say the classical oracle model, you're assuming that the adversary can only access a certain oracle classically. Is that what it means? Or?
No. By classical oracle model, I mean in the construction, like the construction is also allowed to include oracles that compute classical functions, but the adversary is able to query it in superposition.
Okay. Thanks.
Mm-hmm. Was there another question?
Yeah, so I just want to like understand basically like the newer part. So basically, like the newest thing is that now you show how to like sort of like get rid of those classical oracles in the previous work for node circuits that still relied on having this access to these classical oracles, and then you just show that you don't need those in fact. Like I think they were using like this very structured crosset oracles, if I recall correctly, right?
I don't remember the oracles they use, but we still use classical oracles.
So then maybe I got a bit confused of like what is the difference between the two results with like pseudo-deterministic circuits, like the previous ones you mentioned, the 2021 and 2023 one.
BKNY?
Yeah, so yeah, I guess BM and BKNY.
Okay, so BM only obfuscated null circuits. We
Mhm.
get more expressive class pseudo-deterministic circuits.
Yeah,
But BKNY already do that. The only thing that the difference is that in their obfuscation was quantum. So the obfuscating algorithm has to be quantum, and
I see.
the
So
obfuscation
BM
itself.
was using BM was outputting like something classical, but not just for like the full class of deterministic quantum circuits.
Yeah.
And BKNY still outputted something quantum.
Yeah.
I see.
Yeah.
And what was the state, like the quantum states that BKNY was concretely outputting? Like, was it like still quite structured states that you could?
So they were like coset states, essentially.
Mhm.
Yeah. So that's the part we kind of dequantize.
I see. So you basically show how to kind of like delegate the preparation of these coset states. I see. Okay.
Yeah,
Thank
exactly. Okay. So, so our results, what do they mean in the context of delegated quantum computation? Well, this is a setting where there's a quantum server, a classical client, and the classical client wants to perform some computation on the quantum server, and there are a bunch of like things you could ask from a protocol that allows you to do this. You could ask for blindness, which means that the quantum server should not be able to tell what computation it's being asked to do. You could ask for verification, which means that the classical client is actually able to force the quantum server to doing exactly what it wants to do. Otherwise, it'll be able to detect. Succinctness means very low communication. You could hope that communication is low and also non-interactive. So client sends one message and server sends one message, and that's it. And then finally, you could hope to build your delegated computation scheme from as few ingredients as possible. That's both in terms of assumptions and also like what kind of model you're using. So whether you need like classical oracles, for example. So, this was the previous state of affairs, and in our work, we get almost everything except for the last column because we need the classical oracles. And this is, this follows from the publicly verifiable QFHE scheme that we get. Okay, so with that, let me dive into our techniques. Our construction has, a lot of moving parts. So let me lay out a roadmap that will hopefully make it easier to follow. So our goal is to obfuscate quantum circuits with the classical algorithm, classical obfuscating algorithm. And as our title says, we do this by constructing a publicly verifiable QFHE. And this transformation is kind of folklore even in the classical crypto literature, and I'll show you effectively what this is. And then it turns out that to build this publicly verifiable QFHE scheme, what you need is this other object called publicly decodable commitments to quantum states, classical keys. That's a mouthful. I'll explain it when we get to it. But this transformation is not at all obvious. So it's a result of a long line of work culminating in V can Y. And I'll give you some intuition, but I won't focus too much on the details. And so our main contribution is to construct this object, the commitment scheme. Okay, so our work should really be viewed as a dequantization of this previous work, V can Y, who constructed quantum obfuscation for the same class of circuits. And they did this by constructing publicly verifiable QFHE, except that the client had to be quantum as well. And they were able to do this by constructing these commitment schemes, but the keys that the first party sends are quantum. So really, we're trying to dequantize V can Y.
So it's a very dumb question. So what is publicly verifiable QFHE? QFHE, I can understand that you can compute on encrypted data. What are you verifying?
I think that is the next slide.
Shoot, sorry. Okay. Sorry.
Yeah, okay. So yeah, all these boxes and arrows, I haven't explained anything, but I'll define them and when we get to them. Okay, so let's look at publicly verifiable QFHE, right? Ignore the publicly verifiable part for now. Just think of QFHE, or quantum fully homomorphic encryption. It's a cryptographic tool that allows you to outsource quantum computation while keeping your inputs private. Right, so in the setting, there's a classical client with some input X, and they really want to compute some quantum circuit Q on this input X, but they don't have a quantum computer. There's this quantum server that is actually able to compute Q, but the classical client doesn't trust the server with its input X. So what QFHE does is it allows the client to encrypt its input into a ciphertext and send only the ciphertext to the server. And now the server, the magic of QFHE is that the server is actually able to compute homomorphically this circuit Q on the ciphertext C, like under the hood of the encryption, to get this different ciphertext CT prime. And now when the client decrypts CT prime, it will get the output of Q on X. So due to this breakthrough work of Madhav in 2018, we know that QFHE exists, assuming the quantum hardness of learning with errors. Okay, so that was QFHE. When you add the publicly verifiable part, what does that mean? That means that when the server is evaluating, doing this homomorphic evaluation, it not only produces the ciphertext CT prime, but it also produces a proof pi that is supposed to convince you that CT prime was computed honestly by evaluating homomorphically Q on the ciphertext CT. And moreover, given all this public information, so the public key, ciphertext, CT prime, and the proof, and also this circuit Q, anyone should be able to verify whether this proof accepts or not, whether the client will accept the proof or not. In particular, even the server should be able to verify. What that means is, I guess one thing to note is that the verification algorithm does not take in the secret key of the QFHE scheme, right? So that's why it's like public verification. And the guarantee is that, even if the server is given Oracle access to this verification function, it will not be able to come up with a cheating proof. Like that's what public verifiable QFHE needs.
And so
Okay.
the verification is just checking that it has been evaluated correctly. Obviously, the server still doesn't know, for instance, what the evaluation itself was.
Yes, exactly.
Right. Okay. Okay.
Exactly.
Okay. Cool.
All right. So why does this publicly verifiable QFHE suffice for obfuscation?
Sorry. But before you go on, do we know such a scheme with like everything classical? In the sense that, I suppose that you're computing a classical output using a quantum circuit. Is it the case that all the strings being exchanged during the interaction are classical?
Oh, you're still hoping for a quantum circuit?
Yeah. I was wondering, like, so we have classical quantum FHE, right? That's what Mahadev did. Like, of course, we knew how to do FHE with quantum ciphertext.
Yeah.
So now I was just checking if publicly verifiable QFHE is also with everything classical, like in
Yes.
terms of what is sent. Okay.
Yeah. So So for us, when we want to get classical obfuscation, we want everything to be like all the communication, everything that the client does should be classical. But what was previously known is quantum client.
So you build this primitive, is it?
Yeah. Yeah.
No. Okay, that is so cool. Okay, thanks.
Yeah. So why does publicly verifiable QFHE imply obfuscation? If if you've seen this before, the two words that'll help you are verify and then decrypt. Okay, so concretely, what is happening? The obfuscation is as follows. You're given as input some circuit Q, and first what you're going to do is just encrypt the circuit Q under this QFHE scheme. And then you'll also prepare this oracle O that works as follows. It takes as input some input X, an evaluated ciphertext CT prime, proof pi, and then it does this verification procedure. Prime was honestly computed from CT by evaluating this universal circuit with input hard-coded to X. Okay, so let me say this in a few more words. So this circuit univ sub X, that's the universal circuit. So the universal circuit is going to take as input both a description of a quantum circuit and also like an input to the quantum circuit, and as output it'll produce like Q on X, Q of X. So univ sub X is going to hard code the input wires to this input X. So now it only takes in as input this Q and outputs Q of X. So that is the cipher, that's the circuit that we're homomorphically evaluating. And this makes sense because the ciphertext is a ciphertext of Q. So the Q is like what is being fed to the universal circuit. Okay, so you verify, and if everything was fine, you're going to output the decryption of CT prime, of the evaluated ciphertext. And that's the obfuscation. So it consists of the public key, the ciphertext that encrypts Q, and this oracle O. And to see why this works, let's look at how you're going to evaluate the obfuscation. So you have this obfuscation Q hat, and you're trying to evaluate it on some input X. So what you're going to do is parse it, and then evaluate this universal circuit homomorphically on the ciphertext CT. And then you'll get the CT prime, the evaluated ciphertext CT prime, but also a proof pi. And now you feed all of this to your oracle that came with the obfuscation. And since you did everything honestly, the verification is going to pass, and it'll output the decryption of CT prime, which is Q of X. Right? Okay, so one thing to note is, the obfuscation here contains And this is okay because, our assumption was we have ideal obfuscation for classical circuits. And we want to.
Right, so that's why it's okay to have like the secret key somehow in the program, right? Otherwise, this is not a normal thing to do. So that's why you need the classical Oracle obfuscation thing. Is that correct? Am I getting it right?
Yeah. You definitely
Okay.
do not want to give this program out in the clear. That would be.
The decrypt, right? The verify is fine, right?
Yeah, the verify is fine. But like this whole verify then decrypt, like that's the program that this Oracle is implementing.
Right, and the whole thing is classical. That's the key part.
Yeah.
That we needed from. Okay, thanks.
Yeah, exactly. And we can now sort of see why we need a publicly verifiable QFHE scheme. Right? Suppose this was not publicly verifiable. That means that, after repeated calls to verify, I'm actually able to find a bad proof that, accepts on an incorrect evaluated ciphertext. Okay, so then what a bad adversary could do is, given this Oracle O, right, in practice, it basically has access to this verification Oracle because it can, it'll be able to tell whether it accepted or not. So, okay, so it has access to the verification Oracle. So then you can imagine, okay, it comes up with this bad proof that accepts. And okay, in the extreme setting, maybe it comes up with a proof pi star that accepts when the ciphertext CT prime is actually the original ciphertext CT itself. Right? Then when it feeds that proof to the Oracle O, what it's going to get is a decryption of CT, which is just Q in the clear. That's like completely killing the obfuscation scheme.
Sorry, I missed a little bit of why we had to have verification public. So what happens if verify was also with the secret key, and then we used what you were saying, we used the classical decryption, sorry, the classical obfuscation on also verify with the secret key. Like, so in any case, we have some secret key, right, in the program for the decrypt step. I'm not sure why it is crucial that the verify step needs to have a public key. What happens if that was also classically? How does it? That was also SK instead of PK. What breaks?
What breaks? I guess in the setting where okay, so I guess there is some leeway since you're giving all of this as an oracle. You can imagine maybe the verification function itself uses the secret key in some way, but if it only uses the public key, then you know for sure.
Oh, you're saying that it might still be secure. We just don't know for necessarily.
Yeah.
Is that okay?
Yes. Yeah, unless I'm missing something. Yeah.
Okay. And then what you just explained, I sort of still didn't fully understand. Then the attack you're describing also applies here, right? Because the obfuscation does tell you whether or not it succeeded at verifying. Oh, you're saying if you decrypt without? No, okay. I think I misunderstood. So sorry, can you explain again what the point was? Like what the attack is and for which situation?
Yeah. Okay. Let's say that the let's say the QFHE scheme was not publicly verifiable. What that means is that after repeated calls to verify, I'm able to come up with a proof that, cheats, a cheating proof that is going to be accepted by verify.
Oh, I
even
see.
though
Okay.
it's
I got
incorrect.
it. So just to make sure that I'm following, so you're saying publicly verifiable basically means that from the verification oracle, you cannot extract any information about the inputs. I guess this is what you were saying when you were defining public verifiability, right? That was one of the. So maybe that's where the publicly verifiable part becomes important. Okay. I think it makes sense now. Sorry. Thank you. I got confused. Okay.
All good. Not just not able to accept, not able to extract the input, but also not able to produce a bad proof. Not able to then, like for example, you could imagine a setting where I'm, I don't know, taking a test, and then I maybe it's like a multiple choice. So I try it a bunch of times and I get back the answer. Like I get back whether I got it correct or not, right? And then so that improves my success probability like over repeated tries. So like that's the kind of thing that we want to avoid here. Okay.
But that is unavoidable, isn't it? Because if you have public verification, then obviously you can check a bunch of things. I guess the point is that the space of the ciphertext is exponential, so this would not really make any difference, or unless I'm missing something.
Yeah, that's yeah, the guarantee of public verifiability is that like that's the guarantee of public verifiability. Even
I see, got it. Okay.
Yeah, even after access to the verification oracle, repeated access to verification oracle, I'm not going to be able to come up with a cheating proof.
Right. Got it. Okay, thank you.
Yeah. Okay, so we just saw this like arrow that goes from publicly verifiable QFHE to obfuscation. So now let's look at the next arrow. For that, let me first define what this is. So I need to describe at least 3 things. Commitments, how do you commit to a quantum state, and what does publicly decodable mean? Okay, so commitment is a very foundational object in cryptography that it's like a protocol between a sender and receiver that forces the sender to commit to a bit B so that it can't later change its mind. So it's like the sender, puts the bit B in a box, locks the box and sends the box over to the receiver. And then at some later point, the receiver says, okay, I want to open the box. And the sender does some opening procedure to get like an opening key U. And then the receiver opens the box to get the bit B, right? And at this point, it can check, okay, when you opened in the second message, when you claimed your bit was B, when I open the box, I can check, okay, you were not lying. And this process is called verification. Okay, and I guess in a lot of commitment schemes, it's useful to have this first message where the receiver sends a commitment key. It's kind of like a setup. Okay, so what does it mean to commit to a quantum state? Right here, let's think of the setting where there's a classical receiver, but a quantum sender who has this state psi that it wants to commit to. Same idea. We want to somehow commit to this state and later open it. But since like the classical receiver is, classical, it can't really read this state. So the meaningful thing to ask is commit to measurement outcomes of these quantum states. Right? So the syntax is, okay, quantum sender has this state, it commits to it, and gets some classical part, but then also maybe some quantum residual state. And then the classical part is what it sends to the receiver. And then at some later point, the receiver says, okay, I wanted to measure the state in the standard basis or in the Hadamard basis. And then at this point, the quantum sender performs some opening operation that's supposed to, mirror measuring in the standard or Hadamard basis and get some opening information U. And now finally, the receiver is going to sort of decode this opening to interpret it as a measurement outcome in the basis it asked for.
And is it true, like is it just for illustration that you're saying standard or Hadamard basis, or do we know such things for arbitrary basis measurements?
I see. I think maybe there's some recent work. Okay, so originally people were interested in studying standard and Hadamard bases.
And for crypto, I think that's cool.
For crypto?
Sorry.
Yeah, but then I think more recently there's been some work that generalizes to other bases as well.
Thank you. Sorry.
And sorry, maybe just to understand. So basically, is the idea to now try to use these commitments kind of like for every stage of the evaluation, like inside the QFHE, is the point to try to kind of like commit at each step, like after each evaluation of a gate in the full circuit?
No, yeah, so I'll maybe have a slide on this later, but I'll say a few words. Like the idea is similar to what happens in CVQC, like classical verification of quantum circuits. You perform some computation, but then you do it like you compute the history state. And then at the end, you like measure in some random bases to verify.
Yeah, I see, but I think like what confused me a tiny bit is that still like the verification or like this decoding requires using some sort of like secret key, right? Or like some, I guess like decoding key, how you call it here. So, so this is still not in the publicly verifiable setting, right? Like not everybody can check these outcomes.
Yes, I'll say that in the next slide. So, you know, the property that we want for commitments to quantum states is that roughly the cheating sender should not be able to choose what measurement outcome it opens to. That's the vague intuition you should have. So now, what does publicly decodable add? It means that, you know, this binding property holds even if the cheating sender was given access to this decoding oracle. Yeah, okay. So why does this commitment scheme imply publicly verifiable QFHE? Well, as I was sort of vaguely alluding to earlier, the approach to classical verification of quantum computation is usually as follows. The server prepares like a history state, which you should think of as the traceable computation. And then measuring the history state in like standard and Hadamard bases suffice to verify, okay, that you actually did the computation correctly. And the way that like we're able to, okay, so measuring the history state is a quantum thing in like two different bases. That's a quantum thing. Verifier does not have quantum. So how do we get a classical verifier? What these schemes usually do is that the server commits to the history state, and then later it's forced to measure honestly. And since this commitment scheme worked with like classical receivers, you have a classical verifier.
Is it like the ground state of a local Hamiltonian, and then you want to measure the local Hamiltons in X or Z? Is that what you're okay?
Yeah, exactly. And so you can sort of imagine, you know, publicly decodable commitments to quantum states imply public verification. That's the high-level intuition. And this template was, you know, formalized and basically come up with in BKNY. And it's, yeah, this transformation is like not at all trivial, and it took a lot of interesting ideas.
So can you explain a bit like what is public and like in the context of commitment? I think I missed like the last part about.
Yeah, so it's what you said actually. You want the binding property to hold even when the quantum sender has access to the decoding oracle. Like in general, does that make sense or?
Yeah, sorry, I'm still trying to like parse this for one moment to understand how can this still be achieved.
Okay, yeah.
To me, it sounds like a CCA sort of security, right? That you're giving access to decryption and it's still secure. But maybe I'm missing something.
Yeah, I guess in general, this should not be possible. Like if you're given access to both the X and Z decoding oracles in, yeah, if the sender is given both access to both X and Z decoding oracles, this should not be possible in general. But like I kind of didn't want to include this in the slides, but I'll say it. A slight weakening where before the sender sends the commitment, it has access to both these oracles, the X and Z decoding oracles, but after the commitment, it has access only to one of the decoding oracles, the Z decoding oracle. And this suffices to get,
Yes.
yeah, this is the notion of public decodability that we want, and it suffices to get publicly verifiable QFHE. And like, that's what we built.
I see.
Yeah, because I was just a bit worried that, okay, I guess like you try to start with like some unclonable state, like the point of committing. But then I was just worried that, okay, even if you get only one bit by this decoding, if you query it sufficiently many times, that would maybe tell you like enough information about the commitment in the other bases. But okay, I guess you're saying that you're restricting the access after this stage, so that's what prevents it.
Yeah. Mm-hmm. Yeah, exactly. But yeah, I won't make that distinction in the rest of this talk.
And sorry, you also mentioned. Oh yeah, I'm unmuted. Okay, sorry. And you also mentioned that this arrow is very non-trivial, but of course you gave like a cartoon sketch.
Yeah.
So is there like some specific thing that breaks, or it's just formalizing the whole thing it turns out to be difficult?
Formalizing the thing turns out to be difficult, and also, I guess there are two main issues. So we have good classical verification of quantum computation for, pseudo-deterministic computations, things that are in VQP, but not sampling circuits. And the thing we want to verify is this QFHE evaluation circuit. I think that's the computation we want to verify. And that is actually a sampling circuit. So we do not have good CVQC schemes that verify sampling computations with negligible error.
Right.
But yeah, but this QFHE evaluation computation is something more controlled, in the sense that since we only care about evaluating pseudo-deterministic circuits, like once you decrypt the sample that you get from the QFHE evaluation, you get a deterministic output. And so PKNY use that fact to sort of, bypass this negligible sampling soundness.
Right. So this is why you're restricted to pseudo-deterministic circuits in your
Yeah.
whole thing, right? Like if that weren't the case, like if you had like some way of verifying the circuits, I guess then the entire scheme probably goes through with this public FHE.
We'd have to check, but that would, yeah.
Depending on the details of the scheme, right? Of course.
Yeah,
Okay.
yeah. Yeah, so that's one barrier.
Okay.
And the second barrier, actually I'll get to, like constructing the public commitment scheme is not easy, or it needed like a new idea.
Yeah, for sure.
Yeah, like,
Okay.
yeah, so it's some nice ideas were there. Okay, so we construct this last object, and okay,
so
so
just out of curiosity, I feel so bad, but I don't know when I will ask later. But
Yeah,
this is it sort of equivalent? So you had an arrow, right? Can you show the arrow slide? I sort of didn't manage to.
Yeah.
So publicly verifiable QFHE with classical client, does it say anything about commitments?
Ooh, interesting.
Is it? No.
I don't know. I haven't thought about it, but the first thought I have is that I guess public verification of QFHE for only pseudo-deterministic circuits, that's like a classical output thing. Yeah, but the commitment thing, the commitment is like you're committing to a quantum state and you're measuring things that are not at all pseudo-deterministic. So yeah, I don't.
So it may be potentially more general, yes.
Yeah, so I don't see an immediate way to go backwards, but
Okay.
Yeah, maybe
Thanks.
there's something clever you can do. Yeah.
Thanks.
Okay, so this is our goal, this publicly decodable commitment scheme to quantum states. Okay, if you've thought about classical verification of quantum computation, the first thing you're going to try is, can you use the Madhav style commitments? But the problem is these turn out to be not publicly decodable. Given access to the Hadamard decoding oracle, actually, it completely breaks. But BKNY did have a solution. They came up with publicly decodable commitments only with quantum keys, right? So, and this is what gave the quantum keys is what gave the quantum part of the obfuscation to pseudo-deterministic circuits. But how do they do it? Their main tool was to use subspace states instead of the Madhav trapdoor copy functions. And slightly more concretely, they use this property that I'm going to call revocable swappability of these subspace states. Okay, small note, in the paper we call this property delayed collapsing, but I think both of them have useful intuition. So in the talk, I'll use this term. Okay, so to proceed, we'll have to take a detour and talk about subspace states and their properties. Okay, so subspace states were first introduced by Anson and Cristiano in the context of, I think, quantum money, but actually, I don't know. Maybe quantum money or copy protection. But the idea is that there's an unknown subspace state in ambient dimension F2 to the lambda. And the dimension of this unknown subspace is half the total dimension, so lambda over 2. Let's further assume that this you can partition this subspace into two halves. One is S0 and S1. S0 contains all the vectors whose first coordinate is 0, and S1 contains all the vectors whose first coordinate is 1. And so for simplicity, let's assume that this subspace is going to be balanced. So these two sets, these two cosets really, have the same size. Okay, so if I give you lambda over 2 random vectors in this subspace S, with good probability, they're going to be independent and you can fully learn what S is. But if I gave you this subspace state, which is defined as the uniform superposition over all the vectors in S, so it's an even superposition of S0 and S1 vectors, turns out that this state hides the subspace very well. In particular, it has this interesting collision resistance property. So you cannot find both a vector in S0 and in S1. And this holds even if you're given access to these oracles, which sort of additionally leak more information about the subspace. So what do these oracles do? They're basically oracles that are like indicator functions on these subspaces. So O sub S just checks whether the input is in the subspace S, and O sub S perp checks whether the input is in the dual subspace. Okay, so you can think of this as hiding the subspace very well. You can't even find two vectors in the subspace. Like you could find one.
This is given sorry. This is given access to one copy of the state, or okay,
Yeah.
Is it robust to multiple copies as well, or
no? Given two copies, you could measure both and hope.
Or you'll probably get something with a probability of 2%.
Yeah.
Next.
Yeah, with probably half you'll get one in each or something like that. Yeah. And then another interesting property that these subspace states have is something I'll call swappability, which means that you can use this dual oracle to sort of swap between S0 and S1. There's like a nice calculation you can do, and I won't say anything about it, but it sort of allows you to freely swap between these two states, ket S0 and ket S1. Okay, so that was a lot of information, but the takeaway is that the subspace state is uniform superposition over all the vectors in the subspace. And it's an even superposition of the vectors that start with 0 and start with 1. And these states have nice properties that they hide the subspace very well. You can't even find two vectors in the subspace. And given this additional Oracle OS perp, I'm actually able to swap efficiently between S0 and S1.
And is it that we need one invocation of the Oracle for the swappability thing, or I don't think it matters. I was just curious. Sounds like some kind of reflection. Okay. Thanks.
Yeah, it's one. I think it's just like a Hadamard, apply the Oracle Hadamard. I think that's it. Yeah. Okay, so these properties give rise to very interesting applications. For example, signature tokens. So these are signature schemes, but they're more than that. They also have this additional property that a signer cannot sign both a 0 and a 1. So they're sort of like one-time signatures. Right? And these things are impossible to construct classically because, yeah, like if I could sign 1 and if I had the option of signing 0 in the beginning, then I can also do that after signing 1. But quantumly, with these subspace states, because of no cloning, it turns out you can construct these objects. So what is the scheme? The key that the signer gets is going to be this quantum state ket as 0, along with these oracles OS and OS perp. And to sign the bit 0, the signer is simply going to measure this state in the standard basis and get a vector that starts with 0. That's the signature. And to sign a 1, I'm going to use the dual oracle to swap from S0 to S1 and then measure in the standard basis. Okay, because of this collision resistance property, I get for free that, the signer cannot sign both the 0 and a 1. And because like this collision resistance property holds even when everyone has access to these oracles OS and OS perp, verification simply checks that, okay, your signature is a vector in the subspace and the first coordinate is equal to the message. Okay, so we got signature tokens from subspace states, and this is already a really magical primitive because it's not possible quantumly, but even more magically, you can dequantize. Yeah, not possible classically. Yeah, sorry. But even more magically, you can dequantize signature tokens in some sense. And what that means is instead of the verifier actually sending the quantum state over to the signer, this primitive that's called one-shot signatures allows the signer to sample its own unknown subspace along with the oracles. So for us, let's just think of the verifier sending an oracle F to the signer, and the signer then uses this oracle to sample its own unknown subspace that corresponding to some serial number, and it also is able to generate these oracles OS and OS perp, all the while it does not know what S is. So it's really cool. And this still satisfies the properties that there's collision resistance. You cannot find both vector in S0 and S1, and you can always use this dual oracle to swap between S0 and S1.
I'm confused about like a previous point. So if I understood correctly, you are saying that BKNY show that you can construct these public decodability commitments just assuming costed states, so like just by relying on costed states, if I understood correctly your point. So I guess like I have like two questions. So one, is it the idea that as opposed to just having like these closed states now, because you have like these much larger subspaces, that's why there is no attack, that basically even if you query this verification oracle, you cannot trivially recover both an element in the two spaces. Is that's why they need to go beyond close-freeness, like beyond these two elements for position.
Yeah, exactly.
And secondly, like you were saying that the main drawback is that they were using like sending these quantum states, but couldn't they have just do like a QFHE to prepare these cosset states? Like why just sending them when you can just prepare these states like with classical communication?
I see. There is definitely something that goes wrong, but dual oracles. Okay, I'll have to think exactly what goes wrong here, but
But couldn't you do everything under the hood then of the FHE if you're also sending the one-shot signature?
No, but I'm not using one-shot signatures. I'm just to construct those public decodability. If I it suffices to rely on these cosset states. Instead of me sending those cosset states, I can prepare them using QFHE. Like I just like using classical client QFHE. I just pick those two subspaces, and I can prepare the state without him knowing what are S0 and S1. And even if it has access to this decoding oracle, it's still not sufficient to recover both elements of S0, S1, or the dual, or whatever test you perform there.
But under the hood couldn't. Sorry.
Okay, so I guess what goes wrong with this QFHE template is actually there is some work that quantum money without sending. Yeah. But this I think needs some interaction. Like you construct the subspace state with QFHE, but then the verifier doesn't know what the one-time paths are, because that's going to be some randomized thing. So then, so then you need to send me the evaluated ciphertext back. I need to decrypt the one-time paths and then create these oracles, OS and OS-perp.
But isn't it the same as the equivalent of you sending me like the commitment to now be this shift that I would then figure out? Because even in like Mahadeb, we have like the image Y, right? That acts as a commitment. So now instead you have like this shift that comes from the QFHE, no?
The QFHE evaluation itself is going to be randomized. So
yeah. But I'm just saying that after the evaluation, you now have like these subspaces as you want it, and some random shift. And I'm saying that those random shift you would send along your commitment. Like when you commit to something, you would also send this random shift.
I see.
Like the encryption of this random shift, yeah.
Yeah. Okay, so I guess you also need these you need to construct these oracles OS and OS-perp. And for that, you need to know what the one-time path keys are. So there is like one round of interaction you need to do. I think if you try fiat chimering that, my guess is that it becomes insecure.
Okay.
Yeah.
Can I ask something? Could you say something about these subspace cossets? Like something more? I don't know what are these cossets and how are they involved here?
Yeah. So I guess these subspace states are, these uniform superpositions over all the vectors in some unknown random subspace. And they have properties that hide the subspace very well. So if given just one copy of the subspace state, you're not going to be able to learn what the subspace is. In fact, you can't even find two vectors in the subspace. This is like no cloning, but like taken, yeah, in a very useful way. Like this is a very structured state that you cannot clone, and you can like get very minimal leakage from. I guess these subspace states like behave well in both the standard and Hadamard bases, because in standard basis it's like just a superposition of all the vectors in the subspace, but in the Hadamard basis it's a superposition over vectors in dual. And so that plays nicely with, you know, these verification schemes that want you to measure in both standard and Hadamard bases. Does that help?
Yeah, but so I meant the coset, subspace cosets.
Oh, okay.
So the coset aspect of it that I was curious.
Oh, sorry. Okay, got it. The coset states are basically you just shift the subspace states by a random Pauli, by a random X and Z. And okay, I guess historically they were useful for going from, I think, oracle model constructions to plain model constructions, but they kind of play a more like baked in or inherent role when you're constructing one-shot signatures. Yeah. But yeah, but like if you look at the construction for one-shot signatures, it's not clear how to use subspace states to get it, but coset states allow you to.
Thank you.
Mm-hmm. Okay, yeah, but for this talk, I'll just simplify and think about subspace states.
I also wanted to quickly mention that we have about 15 minutes. I think.
Okay, cool.
We asked too many questions. I'll try to let you proceed without too many interruptions now. Sorry.
All good, no worries. Do you know where I was?
You were explaining one-shot signatures in the quantum setting, and
But I think
it's just the next slide.
Yeah, you
Okay,
can finish
okay.
the slide and yeah.
Oh,
that's
okay, got it. Okay. Okay, so to summarize, subspace states have these nice properties, collision resistance, swappability, and these collision resistance holds even in the presence of these verification oracles, OS and OS perp. And these allow you to get interesting primitives like signature tokens and even dequantized signature tokens, aka one-shot signatures. But for us, we want to construct these publicly decodable commitments. Okay, so let's look at what BKNY does to make these commitments. Alex already sort of sketched this construction, but the keys are this subspace state along with these oracles. And the sender has, let's say, one qubit, a quantum state, alpha ket 0 plus beta 1. So now using this dual oracle, it can prepare the following state. It prepares psi prime, which is 0 entangled with S0 and 1 entangled with S1. And now at some later point, the receiver asks, okay, can you open in the standard basis? Now what the sender does is just measure in the standard basis, and then it'll get a bit B and a vector S. And the receiver just checks that the vector is in the right subspace. So that's standard basis measurement. And Hadamard basis measurement is similar, but you know, this is a completely insecure commitment scheme. It's not at all binding, because at the point the sender is asked to open in the standard basis, they still have access to this OS perp oracle. So you can still sort of freely swap between S0 and S1. So it doesn't really matter what state it committed to. It can basically choose the measurement outcome it wants to open to. And also, you know, syntactically, in this picture, no commitment was sent. So, you know, it has no hope of being secure. But okay. Okay, so the key idea that BKNY has is you need some way to sort of ensure that you get only one-time access to this OS perp oracle. And you use this to construct this committed state, but after that, you lose access to it, right? So, and that's exactly what signature tokens allow you to do. So what they do is, in addition to S0 and like that signature token or that subspace state, they have this additional signature token with a different subspace, T0. And then now your OS perp oracle is going to be sort of wrapped inside this outer signature token corresponding to the T signature token. So now when the sender commits, what it's going to do is it has access to T0. It's going to use that to access OS perp. And then it can prepare this cat S0 plus cat S, like 0 S0 plus 1 S1 state. But then after that, it sort of says, okay, I'm done using OS perp. What I'll do is how to merge the T or like use T perp, OT perp to go from T0 to T1 and then measure it. So my commitment is going to be a vector T1 in the subspace T1. So now at this point, I've given you proof that I actually don't have access to T0 anymore because of like collision resistance. And now when I open in the standard basis, I don't have any access to T0, so I can't access OS perp. So, all I can do is measure the state in the standard basis and give you the bit and the vector. So, it seems to satisfy binding. And the thing that the security analysis that you want to do is show that subspace states satisfy this revocable swappability property. What that means is this game is secure. So given ket S0 and these oracles, at this point I can freely swap between S0 and S1. But when I take away the OS perp oracle, and that's sort of done using this outer signature token that gives like one-time access to OS perp, then after that I can no longer swap between S0 and S1. And so this property I'll call revocable swappability, and this is what gives rise to publicly decodable commitments. Okay, but the problem here was that the commitment keys are quantum, and this gave rise to a quantum obfuscation scheme, which is, what we were unhappy with. So there is a natural thing you could try to do is to use the Shmeli-Jandry signature, dequantized signature tokens to sort of go from these subspace state communication keys to classical keys, right? And so, okay, you could try doing that. But then like the guarantees of these one-shot signatures is actually not enough, right? All SC proves is collision resistance. You can't come up with two vectors in S0 and S1, but it doesn't say anything about this revocable swappability property. So what we show, what our main technical contribution is to show that these one-shot signatures actually also satisfy this revocable swappability property. That is, given this oracle F, I can sample my own unknown subspace and these oracles OS and OS perp. And at this point, I can freely swap between S0 and S1. But then when you revoke OS perp, that's simulated by another, signature token, I can no longer swap between S0 and S1. And this gives you commitments with classical keys. So, our main technical work sort of goes into proving this, and yeah, so this proof gets a little tricky. Okay, so now we have these commitments, and if you didn't follow parts of that, this is kind of the picture I want to leave you with. We know that collision resistant functions suffice to build statistically hiding commitment schemes that are secure against classical adversaries, right? Like I can't come up with two openings because of this collision resistant property. But when you go to the post-quantum setting, when your adversary is quantum, you actually need something that seems a bit stronger. You need what is called collapsing functions, but I'll call it unswappable, which means basically you should not be able to, swap between openings to 0, like coherent openings to 0 and coherent openings to 1. Okay, so it's known that this unswappable property implies collision resistance, but for a while it was, not known whether the reverse was true. And in fact, last year, this work of Shmueli and Chandri came up with these, showed that they're not equivalent, right? So they showed a function that is swappable, but collision resistant. Okay, so what that means in terms of commitments is that if you instantiated a commitment scheme from this function, it's going to be classically secure, right? It's all fine. But suddenly when your adversary becomes quantum, like the same scheme is totally broken. And this is what gave rise to dequantized signature tokens. And so in our work, we showed that, these, the Shmueli-Chandri swappable collision resistant functions can be sort of made unswappable. That is a secure post-quantum commitment after you revoke like this dual oracle. And that's what gives us, these commitments to quantum states. So you need to be able to swap in the beginning to like commit to a superposition of 0 and 1. But then after you lose access to the dual oracle, it becomes actually a good commitment scheme. And now I can no longer swap. Okay, so that's the high-level picture. And to summarize, this is the roadmap. We got these, we showed that the SE one-shot signatures satisfy this revocable swappability property that gave rise to these commitments, these publicly decodable commitments. And this gave rise to publicly verifiable QFHE, which then gives us classical obfuscation. Okay, so let me end with some open problems. The first question is, everything that we proved and most of the previous work only works in this ideal model, right? So we need classical oracles to prove anything about quantum obfuscation. But it would be really nice to show that I/O for classical circuits, like this indistinguishability obfuscation for classical circuits, implies indistinguishability obfuscation for quantum circuits. In the plain model, no oracles. And this question sort of came up earlier in the talk in the beginning. And the second question is, okay, so we were able to get a classical obfuscator for this restricted class of circuits, these pseudo-deterministic circuits. Can you expand that class and get unitaries? And yeah, this seems to be out of the reach of current techniques.
Is it the sampling thingy, or should I not was?
No, all good. Like that's the end.